Have you ever stopped to wonder how your phone can instantly pick out all the faces in a photo? Or how with just one tap an Instagram filter completely changes the vibe of a picture? It seriously feels like magic. But what if I told you it's all powered by one single, really elegant mathematical idea? Well, today we're going to pull back the curtain on that very concept. We're going to demystify the engine that's literally teaching computers how to see. So let's start with something you've probably done a million times, slapping a filter on a photo. It happens so fast, it feels like a digital magic trick, right? An image just transforms in the blink of an eye. You can take a picture that's perfectly crisp and in focus, like this one here, and then, with just one click, you can run a blur filter, and suddenly the whole thing looks soft, dreamy, and kind of out of focus. Or, hey, you can go the complete opposite direction. You can run a different operation that takes that same original image and just makes all the details pop. It feels even sharper, even more defined than it was to begin with. And then there's stuff that's even more wild. You can command the computer to just strip away all the color, forget the texture, and find only the hard edges. It basically turns a full-color photograph into a cool line drawing. So this brings us to the central puzzle, right? Blurring, sharpening, finding edges. These all feel like totally different, almost artistic things to do. How on earth can a computer pull all of this off using the exact same underlying mathematical process? To solve that puzzle, we need one really important clue. We have to learn how to see an image, well, the way a computer sees it. And here's the secret. To a computer, that's not a face, it's not a building, it's just a grid. A big grid of tiny squares called pixels, and every single one of those pixels is just a number that represents how bright it is, usually something between 0 for solid black and 255 for pure white. And this grid of numbers, that's what we call a digital signal. It's the computer's way of taking our complex analog world and translating it into a language of numbers that it can actually work with. It's this grid that lets the magic happen. Okay, so now that we have our clue that an image is just a grid of numbers, we can finally look under the hood at the engine that's driving all these incredible transformations. The secret ingredient, the heart of the engine, is this: a tiny little grid of numbers called a kernel. Now, you can think of it like a special decoder lens. Or, even better, think of it as a recipe. The numbers inside this little kernel are the exact instructions for one specific effect, whether it's blur, sharpen, or something else. And the process itself, it's almost shockingly simple. The computer just takes this little kernel and slides it over the big image grid. It moves one pixel at a time, left to right, top to bottom, until it's visited every single part of the picture. And at every single stop along the way, it does a quick bit of math. It lays the kernel down, multiplies the numbers from the kernel with the pixel values underneath, adds all those products together, and boom. That final sum, that becomes the value for a single pixel in the brand new output image. That's the whole trick. So, for example, look at this specific arrangement of numbers. The 5 in the center, the -1s all around it, that is the literal mathematical recipe for sharpening an image. It's telling the computer, hey, make the center pixel stronger, but subtract a little bit from its neighbors. And that's what makes the details pop. So this is the crucial takeaway. The overall process, that sliding and calculating, it never, ever changes. The only thing that's different between making an image blurry and making it sharp is the recipe, the numbers inside that tiny kernel. And this table just lays it out perfectly. To get a blur, you use a kernel of all ones, which basically just averages a pixel with its neighbors, smoothing it out. To find edges, you use a kernel designed to find really big differences between pixels, like this one, with the big -8 in the middle. It's amazing. Different numbers, totally different results. You know, in the world of artificial intelligence, they don't just call the new image a filtered photo. They call it a feature map. And that name is just perfect, because the new image is literally a map that highlights whatever specific feature, whether it's an edge, a curve, a patch of texture, that the kernel's recipe was designed to find. Now, here's where it gets really big. This powerful operation, it's called convolution. And it is so much more than just a party trick for photo filters. It's actually one of the fundamental building blocks of our entire modern world. I mean, just think about it for a second. This same process is at the heart of computer vision, helping a self-driving car see a pedestrian. It's used in medical scanners to make MRIs and CT scans clearer. And it's not even just for images. It's used to find patterns in text for language analysis and in sound waves for speech recognition. It's everywhere. In fact, and this is the really mind-blowing part, when you hear people talk about deep learning and those super complex neural networks, what you're really looking at are systems built by stacking dozens, maybe hundreds of these convolution layers on top of each other. The first layer finds simple edges. The next layer combines those edges into corners. The next layer finds shapes, and on until it can recognize something as complex as a cat. And it all comes back to that one beautifully simple idea. You just slide a smaller recipe of numbers over a big grid of data. And each time you slide it, you get one new value. It's this amazing process that builds incredible complexity out of profound simplicity. So we started this journey with a simple photo filter, and we ended up at the very foundation of modern AI. This one mathematical tool is how we taught machines to see the basic building blocks of our world. Which, of course, leaves us with one final, pretty exciting question to think about. Now that we've taught them how to see, what are we going to teach them to understand next?